Fine, sir.
Everyone is fine.
Yes,
Good. So, ready for one more lecture?
yes, sir.
Okay, so we've been looking at problems of mixing, and in the last class we saw a little bit about mixing, and then I just started introducing what is segregation. So the first thing we looked at, not in the previous, but the previous to previous class, was that if we take a black box approach, then given any mixture, we can find out what is the current mix state by just taking n samples from different points in the system and then measuring the concentration. That concentration could be either the number fraction or the volume fraction of the species that you're trying to mix into the bulk. So the mean concentration, so if you have xi for n different samples, then the mean value is just given by this, which is the sum of all the concentrations divided by the number of samples n, and S is the standard deviation. And we also saw that if the system is completely segregated, let's say, you are in a situation like this where, your this is x bar and this over here is 0. So in that case, I'm sorry, here let's say this is 1, the concentration here is 1, and the other is 0, and this volume over here is x bar. Then we saw that in this case, the standard deviation is just given by this formula, where x bar, remember, is the mean concentration. In the last class, what I said is that really what we would expect is that for perfect mixing, everywhere you will have xi equal to x bar, so S will go to 0 for perfect mixing. But the problem is, while that may be true, you always have some measurement error. And let's say, for example, you take a sample from your system and that sample has n particles in it, then the least count of the concentration measurement is 1 by n. So as I was saying that, if there are 5 particles, then, your values of xi can only be 0, 0.2, 0.4, 0.6, 0.8, and 1.0. So the least count is 0.2. Because there are only 5 particles, so you can't get a better resolution of xi. So because of that, you'll never be able to reach, in your measurements, you'll never be able to say that S is equal to 0. X will always be something different from 0. And what we said is that the final value of the standard deviation when you have a least count of 1 by n is just given by this formula. And so this S infinity will be 0 only when n goes to infinity. Here n is the number of particles in a sample, whereas over here n, capital N, is the number of samples that you have taken from the system. So in each sample, what we expect that there will be n particles, small n particles. And of course, we only can take a finite number of particles. So if we do a simple calculation, then if x bar is 0.5 and let's say in our sample, every sample we have around 100 particles, then from the formulas that we have put down, then S0 will be 0.5 and S infinity, which is S0 divided by, because this quantity is S0, by square root of n, that will be 0.05. And if you are plotting S by S0 versus time, then in the beginning you start with S equal to S0, so it starts at 1. And at long times, your S infinity by S0 will be 1 by square root of n, which in this case is 0.1. So, the graph will start at 1 and then it will plateau at 0.1. It can't go to any lower value simply because of the measurement error. Now, suppose you want to predict how mixing proceeds. So, if we assume that the particles are similar enough so that there is no segregation, that they don't separate out while flowing, and if the flow is not affected by the concentration of the particles, that is, sometimes if you have particles which have different flow properties, then in different regions you will have different velocities depending on the concentration. So in this model, we assume that velocity is not affected by concentration. And in that case, you will have this as your governing equation. This is the rate of change of concentration. This term is known as the convective term. That is change in concentration due to the flow. And this last term is the change in concentration due to diffusivity. Here D is the particle diffusivity, and we saw that it can be written as just D squared into gamma dot, where D is the particle diameter, gamma dot is the shear rate, and C is some constant. So this way we can, starting with some initial concentration profile, we can actually predict how the concentration will change. And then once we know that, then we can easily calculate all these quantities, like mean, standard deviation, all this can be calculated for the system. Then what we did was we said, okay, let's look at a simple example, which is supposing you have a cylinder which is rotating about its axis, and then you want to study how the mixing takes place in the axial direction. So in this case, the concentration gradient is only in the z direction. So that's why on the right hand side only del squared C by del Z squared comes, and there is no flow in the Z direction. So that's why V dot gradient of C is 0. So this is, you get this equation, which is often called Fick's second law, and that will tell you how the concentration evolves with time. And the boundary conditions are at the two ends, del C by del Z is 0. This means that the flux of particles at the ends is 0. These ends are decided by Z equal to 0 and Z equal to L, where L is the length of the cylinder. And as a simple case, we had taken that, let's suppose C is just that the concentration initially is just given by this cos of pi Z by L. And for this, we found that the solution is given by this. And you can see from here that as time goes to infinity, your concentration will simply go to 0. What does this actually mean? Well, here is the plots of the graph in dimensionless form. On this axis, I've plotted the concentration, and in this axis, I've plotted the dimensionless length, yz by L. And these graphs are for different dimensionless values of the time tau. So this is t equal to 0, then 0.5, 1, 2, and 4. So initially, the concentration is like this. So in this half of the plane, the concentration is positive, and over here it is negative. I mean, you can think of C to be something like, say, this concentration, you can think of this as a dimensionless concentration, and it could be C minus the mean concentration divided by the mean concentration. It could be something like this. That's why in some places it's positive and in some places it's negative. And at time t equal to infinity, C is equal to Cm, so it will C bar goes to 0. So that's what this solution means. But you can see how the concentration changes and it eventually becomes uniform. Everywhere the concentration is 0. which is in this problem, it will be the mean concentration, whatever you started with. Now, this I didn't tell you about last time, but I just thought that I'll show you that in fact this type of thing works. So here, what I'm showing you is actually results of an experimental study, and we are seeing the top view of a rotating cylinder. So we are just looking at the thing from the top. So you just see the top surface, and the initial at t equal to 0, you have red particles on one side and green particles on the other. And then, you essentially rotate this cylinder for a long time and then take another picture after 2 hours, 120 minutes, and then it looks something like this. And then you take it after 4 hours and then it looks something like this. So this is for 3 millimeter glass beads and the rotational speed is 25 RPM. And you can see, initially, so if you look at this, the initial profile is like a step function. If you say what is the concentration of red particles, then it's all over here, all red, and then it's green. But over time, you can see that there is increased mixing. And here is another photograph, a magnified version of this one, and you can clearly see that things are mixed. So now, if you want to get a quantitative, so these are experimental photographs, but you can do what is known as image analysis. So you can actually do computations and identify that, okay, this pixel is red and this pixel is green. And so after image analysis, you can see over here, all the red pixels have been colored red and all the green pixels have been colored green. And from this, at every value of Z, we can get what is the concentration of red particles by just averaging in this direction. So we can divide this into boxes like this. And then, we can get what is C1, C2, and so forth. And so like this, we can get the concentration profile at different times. And in this graph, okay, so here it shows, okay. This is showing the thing, okay. So now you can see how it's been divided up into boxes, and then we calculate the concentrations. And this shows the measured concentration profiles. So here you have the concentration on this axis, and on this side it is the dimensionless distance. And this is different times, 15, 60, 120, 180, 240. And what we have done here is just plotted the predictions of this model, which are the red lines, and the dots are the experimental measurements. And you can see that there is really a very nice match between the experiments and the theoretical prediction. So this idea of writing this as a diffusion problem works quite well. But you can look at also some problems in which involve both flow and diffusion, that is velocity and diffusion. And there we can look at what is, supposing you want to look at the same rotating cylinder, how does the cross-sectional mixing take place? So supposing I have some red colored particles here, then how fast will they mix in the cross section? So for that, we need to know both flow as well as diffusion. And we have already studied the flow, and so these are the equations for the flow. So in the layer, you have these equations, and in the bed, we just have a solid body rotation. And what you are seeing over here are just is a plot of this equation. So these gives you the streamlines of the. Now we can incorporate this flow model into this governing equation which we have written down there. Here now F is the concentration. So you can see del F by del T plus V dot gradient of F is equal to D into del squared of F. So to study this cross-sectional mixing, what we did was we had red particles here and green particles here. They are arranged in this nice way. And then after 0.5 revolutions, after 1 revolution, after 1.5 revolutions, you get these patterns. So why does this happen? Well, because these particles are already in the flowing layer. So as soon as the flow starts, those particles move down and they create this kind of a streak. So these particles, they move down here, giving this streak. And then as you go, for more and more revolutions, you can see that you had an initially sharp interface, but the interface becomes diffuse because of the diffusion of the particles. So this is the experimental results. And over here, you can see the predictions of this model. And there is a pretty good match between the two. And then, if you're not satisfied by just looking at it and saying qualitatively, yeah, the match is quite good, then you can actually measure the concentration profiles. And here, what we have done is that you take off the top plate and then you put in a plate with many holes in there. And then you can measure as a function of the radial distance what is the concentration. So these points are the measurements of the concentration as a function of the radial distance, and the lines are the model predictions. So again, you can see that there is a very nice agreement, and so this equation that I told you for predicting mixing, it works quite well if the assumptions are satisfied. Then what we started talking about was segregation. And here the idea is that, if you have particles which are dissimilar, then they will just spontaneously separate out. And one of the problems that I discussed was this Brazil nut problem, in which if you have a container which has a large particle, then with vibration of the container, the large particle simply rises to the top. If you take a mixture of two different types of particles, where let's say one of them is angular, the other is round, so the angles of repose are very different, then you can get a layered structure like this. And finally, if you have a flow in a layer like this, then what you find is that if there's a mixture, then the particles with the larger diameter rise and particles with the larger density fall. So then if you plot the concentration profile as a function of the height, then what you get is that the heavy particles will come down here, the light particles will be up there, and in between there will be a mixed region. Similarly, the large particles will rise to the top, the small particles will sink to the bottom, and in the middle there will be a mixed region. Okay. So now what I'd like to do is I'd like to just try and explain, why does this segregation happen, and how can we how can we come up with some simple models for this segregation? So this is what I'm going to start off with today. And we'll do some very simple calculations. A lot of this you would have sort of seen in fluid mechanics or whatever, and then you can extend many of these ideas to these things that we're talking about. Okay, so now let me share the screen again. Okay, let me go somewhere closer to, for some reason, okay. I'm going to share the screen again. Okay, so this is the last thing that we were talking about, that the segregation. So now let's continue on this path. And here we look at some models for segregation. And we are today in lecture number 35. So the first thing I want to sort of look at is density segregation, because that is a lot easier to, we'll do size segregation next, but first let's look at density segregation. So we want to look at segregation of equal size particles, but with different density. And the example for this could be steel and glass spheres of the same size. Okay, so you can imagine this. And let's suppose that these particles are flowing down an inclined plane. And to start with, I'll say that there's only glass beads that are flowing. And suppose this angle is theta. Here is your gravity vector. And I'm going to consider only one particle flowing in a sea of all the others. So I'm not drawing all the other particles, but all the particles are of equal size. And let's say that this one has a density ρ1, and the other particles which are there, which I'm not drawing, they have a density ρ2, such that ρ1 is greater than ρ2. So we want to see what will happen to this one particle in this system. And we are really interested in what happens in the direction normal to the flow. So there will be a flow in here as we have done before. So this flow is there, but we are not so much interested in how it moves in the flow direction. We are interested in what is its velocity in the direction normal to the flow. So what is this V1? And let's suppose all the particles have the same volume V. Okay. So now if we just take a force balance of the particle in the direction normal to the flow, so then so what are we assuming before we start taking the assumptions are as follows. So we have a single particle in a fluid of density rho, and this rho I'm going to put it as phi, which is the volume fraction times rho 2. Okay, so the bulk density so if you look at the bulk density of this, it is actually just rho, because it will be rho 2 times the volume fraction. So there's mass of the particles and there's empty space. So the bulk density of the fluid around it is rho. So this is one assumption, that you essentially have just a particle in a fluid. So we can imagine that the stuff outside is just like a liquid. And then we'll say that the particle is falling at its terminal velocity. So what does that mean? Now, obviously, since the density ρ1 is greater than ρ2, so then the particle will want to sink. It will be falling down. But since the granular material is so viscous, so dissipative, that the motion is going to be very, very slow, and so the particle will be at its terminal velocity. There will be no acceleration. So the acceleration is equal to 0. So this is what is required. And then if we do a force balance, then what you get is if you look at what is a force acting downward, well, that is going to be the weight of the particle. So that is ρ1 into the volume of the particle V. So that is mass into G times cos theta. So that is just mg cos theta, or m1g cos theta. So this is the weight of the particle. And that is what is acting downward. And since there is no acceleration, this force must be balanced by the upward forces. So what are the upward forces? Well, one upward force is going to be the drag force. I'm going to write it as Fd. Because if it is moving, then the other particles are resisting its motion downward. So then it gives you a drag force, that is Fd. And then there is going to be the buoyancy force. Now, why do we have buoyancy force? Well, you have a pressure gradient. We have already seen that in this system, the pressure is zero at the free surface, and then it increases linearly as we go down. And you know that whenever you have a pressure gradient, the pressure, what you will find is that the pressure, total pressure on the upper surface, if you integrate this whole thing, the force acting downward is going to be less than the force acting upward because of the pressure acting below, since the pressure is increasing with depth. So as a result of that, you will have an upward force, which is the buoyancy force that is acting upward. And if we assume that this is just like an Archimedes type of buoyancy force, then that is just going to be the bulk density rho. But now the volume, I'm going to say, is some effective volume times g cos theta. So this is the buoyancy. And what I'm going to say is VE is an effective volume since, and why do I say effective volume? Because the true picture is that here you have your particle with the density ρ1, and around it you have other particles which are of density ρ2. So this is not quite a fluid, and there are all empty spaces. So this ρ1 actually has a size, effective size, that is larger than what is actually the size. But then the question is, how do I get what is this effective volume? Well, I can find out this effective volume very easily by just simply saying that if ρ1 is equal to ρ2, then the buoyancy force will exactly be equal to the weight, right? Because if the particles are all of equal density, then there will be no upward or downward motion. So then the weight of the particle will be balanced by the buoyancy. And of course, F drag will be equal to 0 because there is no motion. So if the forces are balanced like this, then what that means is that in this case, what you will get is that ρ2 into V into G cos of theta is equal to rho, which is nothing but, if we see this, rho is nothing but phi times ρ2. So this is ρ2 into phi times the effective volume into G cos theta. So if we take this limiting case, you can see clearly that everything will cancel out over here. Rho2 cancels, V doesn't cancel, but G cancels and cos theta cancels. And so we are finally left with just that V effective is nothing but the actual volume divided by phi. So here is our final result. And so from this, if we knew what is the drag force, we can easily find out what is the we can easily find out the velocity v1. Now, if we further assume that Fd is given by Stokes' law. Since the viscosity is so high, then you actually have Fd is some constant, I'm calling it C1 into d into eta times V1, where C1 is a constant, d is of course the diameter of the particle, eta is the viscosity, and V1 is the velocity that we want to find out. So now if we substitute for both Fd and Ve in this equation, then what you'll have is rho1 Vg cos theta is equal to F drag, which is just C1 d eta into V1 plus the buoyancy force, which is just rho. Now we know that the effective volume is nothing but V divided by phi into g cos theta. And finally, if we even substitute for rho, which is just phi times rho2, uh, then instead of writing this rho over here, I can just write it as rho2 into phi. So that is the substitution. So again, now if we do all the cancellations, then everything cancels. Oh, well, not quite. But over here, at least things cancel out. And we can find out what is the velocity V1 is just equal to V. I think more importantly, let's write down the first term. So it is equal to rho1 minus rho2 times V into g cos theta divided by C1 into d into eta. So this gives us what we can call is the segregation velocity. So this is for a single particle that is falling in the system. And in fact, if we take the velocity inside, then we can write it in terms of the mass of the particles. And here, what the mass will be given by is, this, then what you'll get is V1 is just equal to m1 minus m2 into g cos theta divided by c1 d eta. So this is just fine. These two are the segregation velocity expression. So this is the velocity with which a single particle will fall. So now what we'd like to find out is supposing we wanted to calculate what is going to be the flux, then the flux of, instead of segregation velocity, if I want to call it as a segregation flux, I'm going to call it as J1, then this should simply be equal to the segregation velocity V1 minus the mean velocity times the concentration of the particle. So this is what is the segregation flux. And if you look at what is this mean velocity, This is just going to be equal to V1 times the concentration of, so let me write down this, the mean velocity, that is, or the average velocity in the system for both particles of type 1 and 2. So that will be V1 times the concentration of 1. This is the mean velocity. So what you can imagine is that this particle is moving downward, but if you want to maintain the density, then all the other particles have to move up. So you basically have V is just equal to V1 times C plus V2 into 1 minus C. But since it's just a single particle moving, then the upward velocity of the type 2 particles is almost equal to 0. So this we can approximately put it as V1 times C. And so where C is the concentration of particles type 1. And so now this gives us the flux J1 is just equal to V1 into C into 1 minus C. And if you substitute for the velocity of V1, then what you will see is that the segregation flux of particles is just so this is for, you can say, the flux of so when we are considering just one particle in the whole system. And what that actually means is that we are considering a very, I'm sorry, I don't know why it's jumping. We are considering a very dilute system where the concentration of the particles is extremely small. So C is extremely small, and so you're only considering the motion of one of the particles. So this is what you would get for the segregation flux. Now we can easily extend this to the case of mixtures, where now you just don't have one particle in the bulk. But let's suppose that we have this same system. So I'll start with the same system, but let's suppose that outside it's not just particles of type 2, but it's a mixture of particles of both type 1 and type 2. So let's suppose that over here the density is just rho times m. So the density is rho m, which is the rho of the mixture, which we'll say is rho m is just equal to rho 1 into C plus rho 2 into 1 minus C. So where rho 1 is the density of particle 1, particle of type 1, and rho 2 is the density of particle of type 2. And again, rho 1 is greater than rho 2. So now you have actually a mixture of particles outside, and you want to consider one particle in a mixture and then calculate what will be the velocity. So in this case, it will be exactly the same thing as before. So there is no difference in the derivation, and what you will now get is, instead of here where we have got rho 1 minus rho 2 as the segregation velocity, we will actually get V1 is just equal to rho 1 minus rho m into Vg cos theta divided by C1 d into eta. So it's the same as this. Is the same as this formula. Only thing, instead of rho 2, I'm putting now rho m, where rho m is actually the mean density for both rho 1 and rho 2. So now what we are imagining is that here you have a particle of density rho 1, and outside you have a fluid which has a density rho m multiplied by 5. So the bulk density is just rho is just equal to rho m into 5. Whereas earlier we were looking at rho is equal to rho 2 into 5. But we have already calculated this velocity. And if we do exactly the same thing, then what you will find is you can write down an identical expression for V2, which will be given by this expression. So again, you'll have rho 2 minus rho n, but the sign of V1 will be different from V2. So V1, since rho 1 is greater than the mean velocity, mean density, rho 1 will always go downward. I mean, V1 will, so particles of type 1 will always sink, because rho 1 will always be larger than the density, than the mean density. And the particles of type 2 will always rise because rho 2 is always less than rho m. So in this way we get the velocities, segregation velocities of both types of particles, and the heavy particles will sink, whereas the lighter particles will rise. And the velocity with which they sink or rise, they are the segregation velocities. Now we can calculate the mean velocity as before. This is just V1 times C plus V2 into 1 minus C. Now we know both V1 and V2. And then let's suppose we want to calculate the segregation velocity of 1. This is nothing but V1 minus the average velocity. And so if you put this in there, you'll see that this is nothing but V1 minus V2 into 1 minus C. And if we take V1 minus V2, then the rho m essentially cancels out, and surprisingly we get an identical expression for this V1 segregation, which is that rho 1 minus rho 2 into Vg cos theta. This is if you subtract V2 from V1. you will get this expression. And then this multiplied by 1 minus C. And so now if you calculate the segregation flux J1, sometimes we write it as J1S also. So then the segregation flux, now I can take the density volume inside. So this just simply becomes M1 minus M2 into G cos theta So what is the segregation flux? That I didn't write down. Just as before, the segregation flux is nothing but the velocity of one relative to the mean velocity. This is the definition of a diffusive flux times the concentration. So velocity into concentration gives you the flux. So this is just equal to m1 minus m2 into g cos theta into C into 1 minus. So this is your expression for the segregation flux. But now this is valid for all values of the concentration. Surprising thing is that it's just exactly the same as before. What we got for dilute and for the concentration, the expression is exactly the same. So this is the segregation flux. So, in mass transfer, you're always talking about fluxes. And so this is you can think of a diffusion flux. And we have talked about diffusion in the previous classes. So that diffusive flux is given by Fick's law. The segregation flux is exactly opposite of the diffusion flux because diffusion tends to mix things, whereas the segregation flux tends to separate things out. And this is the segregation flux, and this is valid for all C. So here we have this, and of course, so many assumptions were made. But in the next class, I'm going to try and show you that, in fact, this type of expression, it works quite well. And I'll try and show you some both numerical simulations as well as experimental results which validate this result. And one other thing is, and one example that I will show you is that supposing, if I go back to this, all this was what we did today, but what we stopped, so we are actually looking at this problem where the light particles go on top, heavy particles go at the bottom. And we have come up with an equation which will help us to predict the segregation flux, which will tell us what is the rate at which the heavy particles go down. But so we can predict this, but you see that there is a mixed region also. So there is pure light, pure heavy, but then there is a mixture also in between. So then the interface region, things are mixed. And the reason that happens is because in addition to segregation flux, you also have a mixing flux, a diffusive flux. I'll call it as J1 of D. this is diffusing. So these, and that is given by JD into del C by del. I can say any variable del C by del. So you actually will have a balance between the diffusion and the segregation, and so in some regions there will be a mixed state, in some regions you have pure, in some regions pure 1, pure 2. Okay, so in the next class we'll do an example to study what would be the concentration profile if you had a certain flow, and in that flow there was a balance between both segregation flux and diffusion flux. So what will be the profile that you will get? So with that, I'll end the class, and now I'll see you next on Thursday. Okay.